Atmospheric Science students, Dr. Shragi and I am ready to start telling you about how we're going to be using the C programming language to be working with files, how we're going to open files, how we're going to read files, how we're going to write files, all that kind of good stuff. In order to talk about files, though, in this way, we have to think a little bit more carefully about what we mean when we're talking about a file. It would be easy to have a misunderstanding about files because we use the word kind of stupidly when it comes to, well, no, it's an understandable misunderstanding. See, on Windows and on Macs, you tend to think of a file as containing something, like a file folder, okay, or a filing cabinet or whatever, and you've been trained to think that way all these years because that's what, you know, the icons on Windows and on Macs and stuff do. But that's actually a bad metaphor. That's actually not what is meant by the word file. The word file actually refers to the sense of the word as in single file, as in all lined up in order. They are all in a single file. And what's in a, like, you know, like these drummers here on this screen in this band here, this marching band, they're all lined up in order. In the same sort of way, in a file on your computer, what's lined up and in order is, well, bits or bytes. Bits. Bits are individual little ones and zeros on the hard drive or in memory or whatever. We say ones and zeros, you could think of them as on and off or whatever. We're getting pretty basic stuff here though. I mean, we're going to work at this more abstractly than this. But there's going to be a long string of these ones and zeros, every one of which is called a bit. So each of these little drummers here could be a 1 or it could be a 0. Each one is a bit. And if you group 8 bits together at a time, that's called a byte. B-Y-T-E, a byte. There are, if you work out, 256 possible combinations of ones and zeros when you have 8 of them long. There are therefore 256 different possible bytes. That's all there is. There are 256 different possible values of bytes. This particular one that's on the screen right now is byte 10001101, and any other combination of ones and zeros, there's only 256 of them possible. And those 256 different bytes have been mapped to a code where a particular combination of ones and zeros, a particular byte, by agreement means the letter A. And then actually a capital A, let's just say. So I've just made these numbers up by pounding on the keyboard, but let's just say by agreement we have decided that 0101101 means A, and 011011110 means B. And maybe 1110101 means new line. And maybe 111000101 means plus, okay? 256 characters have been mapped, each one to one byte. And this code, this idea that we have decided this byte means this letter, or this digit, or this symbol on your keyboard or whatever, has a name. That code is called ASCII. It's an American Standard Code for Information Interchange, ASCII. And when we are working with data files, we're going to hope to work with them in the ASCII format. This is a very simple, straightforward way to work with something that's in a text-type format. It's how text messages before the world of emojis and all that kind of stuff had worked. They were all in ASCII code. Your C programs are in ASCII code, okay? To you, it looks like pound, well, we'll get there in just a second here. This code, though, is how the computer decides, okay, I'm on the hard drive and what I have encountered is a file. The computer's hard drive is reading along and it comes across the beginning of a file. We'll worry about how it did that later. It's going to start coming across a whole bunch of ones and zeros. 110011001111101101. What does that mean? Oh, well, it breaks it down into groups of 8. Here, let me show you. Here's a whole, we just started reading some file. 0100100100, whatever. Big, long. Could be millions of these bits long. Okay? What the computer does is it starts dividing them up into little blocks of 8, each of which is a byte. And then, so I meant like there's a red byte there, and a black byte, and a red byte, and just to kind of illustrate what's going on here. And then each of them, it looks up on the ASCII code, what does that symbol mean? 01001010, it looks it up, and maybe that's pound. Okay? And then it looks up 100111100, and maybe that's I, lowercase I. Okay? And it looks up the next symbol, and maybe that's an N, and then the next one it's a C. And you see what we're getting here. maybe this string of bits means pound include, stdio.h. Again, I didn't actually look up the right ASCII codes for these things. I just pounded ones and zeros on my keyboard. But you get the idea. This is what's actually going on behind the scenes when you open a file. When you open a file, the computer finds the beginning of the file. We'll have to figure out how it's going to do that. And then it starts reading in this file, this stream, this single file of bits, breaking them up into bytes, and then for each of those 256 different possible bytes, looks up what is the ASCII value to make that mean something. Now, when we look at an ASCII file with something like VI, it's already done all that. If I have some file, like in this yellow box right here, maybe this is decoded data.txt or something like that, okay? It's already been converted to ASCII. That file that was on the computer was just a whole bunch of ones and zeros. But VI opened it up, broke it up into bytes, decoded those bytes, and get something that maybe looks a little bit like this. Now, right now, it's just a bunch of numbers. Well, it's a bunch of digits, right? Zeros and threes and fours and decimal places, as well as spaces, which the right word in computer science is that's a token. It's what is breaking the numbers up. We can tell the difference between that first number and the second number because there's a token in between them. It could have been something else like a tab or a comma or something like that. In this case, I'm using a space for my token. If I just had that little yellow box there, that was my file, that's all I had. It doesn't tell me very much. It's a bunch of digits, but I don't know what those numbers are. You need to know what those numbers are. You need to know the format of these data. Okay, in this case, I'm going to tell you right here now, that first number is like a time. Okay? I made this file, and I'm going to tell you that those first four digits are like a time, like hours and minutes. And that second number, let's call that a temperature in Fahrenheit, and let's say that third number is a dew point in Fahrenheit. If I didn't tell you that, though, there'd be no way to figure it out. There's no information in here that would help us with that. Now, it's actually, when I put it up here on the PowerPoint screen, it actually looks a lot like some kind of table, but that's just because that's how I formatted it. In practice, it really is the digit 0, the digit 0, the digit 0, the digit 0, a space, a digit 3, a 4, a decimal point, a 5, a space, a 3, a 0, a point, a 9, and then a new line character to move me to the next line, and then, because that's one of the ASCII codes is new line, and then a 0, 1, 0, 0, space, 3, 3.9, space, 3, 0.8, another new line, etc. It's actually all just lined out. But something like VI knows how to take that and render it. Okay, those new line symbols mean move on to the next line. To read this file then, a computer program that we're writing in C is going to have to be able to scan through this file. Scan in the sense of like scanf. We're going to be using a function to scan to get input from this file. Notice how the values have to be separated. They're separated by tokens in this space. Most of the time in C we use spaces for tokens, but there could be other things. So when we're ready to read that first value, what's going to happen is our function in C, which we don't know yet, is going to read in, it's going to read in an integer. It needs to know that this is going to be an integer, and it's going to then read in until it hits a token. It's going to read in 0, 0, 0, 0, space. Oh, that space is the token. So I've got 0, 0, 0, 0. If I'm told in advance that is an integer, it's going to interpret that as 0 times 10 to the third, plus 0 times 10 to the second, plus 0 times 10 to the first, plus 0 times 10 to the 0th power equals 0. Look at all the math it has to do to come up with the number 0. Okay? Good thing computers are fast. To read in that second value, we're going to have to tell the computer in advance this is a floating point number. Because then it will read in a 3, a 4, a period, and a 5. And it will compute that, then it'll hit a space, a token, and it'll say, oh, I know what this is. Then this is 3 times 10 to the second power plus 4 times 10 to the, 3 times 10 to the first power plus 4 times 10 to the 0th power plus 5 times 10 to the negative first power. And that's going to give me the number, the floating point number, 34.5. Again, think of all the math the board computer has to do to make these things happen. Okay. So you're reading this file, but in order to read the file off of the hard drive, the computer has to actually know where on the hard drive this file is. Where is this file that we're reading? I mean, we have this idea of folders and directories, but that's actually going to be what we're going to learn. It's called a metaphor. I mean, you would be forgiven for getting the idea that there are like territories or areas on the hard drive. Here I have this blue circle here that's supposed to represent the hard drive of your computer. And you would be forgiven for thinking like your files are over here and Dr. Shragi's files are over here, and like if on your own computer, like maybe your MP3 files are over here and these images for your camera are over here. It isn't like that at all. That is not in the tiniest little bit how a hard drive actually works. Files that are next to each other, like in the same folder, has nothing to do with where they physically are on the hard drive. They're just really scattered. They're just any place on the disk that the computer could find room when you saved that file. Two files that might be in the same folder have nothing to do with physically where those bits are on the hard drive. So like in this case, maybe assignment 5 starts at that spot on the hard drive, and maybe assignment 6 starts at that spot at the hard drive. How do we know? Well, in order to open up the file then, you're going to need to know the address of the file on the hard drive. Every little speck of the hard drive of your computer has an address. There's a complicated scheme that the computer uses to keep track of every location on the hard drive. To open up a file, you need to know where is that very first byte that makes up this file. Fortunately, C has a function that gives it to you. It's called Fopen, or Fopen. Fopen. This Fopen function will give you the address on the hard drive where your file starts. So, for example, here's a lovely example of a Fopen command. Fin equals Fopen weather.r. What does this actually mean here? This function file opens a file called weather.dat for reading. R means that it is a file that you are reading. You could have a W there and it'd be a file that you're writing. So if I have a file in my directory called weather.dat and I want to read it, I say fopen or Fopen weather.dat, R. Both of those things in quotation marks, as you can see there on the screen. What this will do is Fopen will use the standard input and output archive to go and dig around on the hard drive and find the first byte, the first bit really, of weather.dat and return the address to that. Fin is then equal to the address of that. This function returns the address of this file on the hard drive. In this case, the address of the file is then going to be stored in a variable which I'm calling fin for like the input file. I was trained when I learned how to write C programs to use fin and faut. Fin for input files and faut for output files, but you could call it whatever you want. But fin is what for file input. Call it whatever you want though. So fin is a variable in this case. It is a variable that stores something. In this case, what it stores is not a floating point number or an integer. What it's storing is an address. And it has a special type. It's not a float, it's not an int, it's a file. Excuse me, it's file with all capital letters. I don't make the rule, I wouldn't have made it that way, but whatever. File, and you write it *fin. Okay, it has to be a big file, capital file, and then *fin. What's that star there, that asterisk in front of there? It is necessary to explain to the computer that fin is what the right word in computer language is that it's a pointer. It points to the place where this file begins. If you didn't tell it that, you'd have to make a change farther down in the program. And so by convention, what we do is we tell the computer up at the beginning, file *fin means that fin is a pointer to a file. So here's a little program, and we'll do some more examples in just a little bit, but like if I had a little main program here where I declared file, declared fin as a file, we could open this file that's called weather.dat, and then we could do things like read stuff and then close the file. The command to close the file is fclose and then the name of the file pointer to the file. Why do I have to close the files? That's a bit complicated. If we were writing the file, if this was a file that we were writing, closing is actually quite important because you have to actually provide, when you close a file that you are writing, it provides information to the file like this is the end of the file marker and things like that. I don't actually know what exactly closing a file does when it's an input file, but it's good habit. Close the files after you're done working with them. The function that we're going to use to actually do the reading of the file is going to be fscanf. Remember scanf? That was the function that read from the keyboard. Fscanf is going to read from a file. It works pretty much the same way. I mean, remember scanf was like, for example, you provide a format specifier like %d if it's an integer, and then ampersand in the variable you want that to go into. fscanf works the same way. I apologize, it rendered a little badly on the screen here. That semicolon should be on the same line. fscanf, provide it with the file pointer you're talking about. This is the file I'm working on. And then %d, tell it it's an integer, and then ampersand the variable that you're trying to read in. Okay, notice you got then just this one additional argument. It's just the address of the file you're trying to read. So for example, here we have some fscanf in this program here. If I had that weather data file, I could use fscanf to read in an integer that would be called time, and then a floating point number that's called temp, and another floating point number that's called dupe, and so on, and then close the file. And we'll do some examples of this live. This could have all been done in one nifty little scanf, by the way. Look what I did on this one here. I used fscanf, fin, %d, %f, %f, and then ampersand time, ampersand temp, ampersand dupe. That was pretty slick. That would work just fine too. We could put this in a loop. We could have done all kinds of things, but just don't open and close the file multiple times. Most of the time you only want the things like opening and closing the file should be outside of the loop, and then the reading of the file should be inside the loop. Because you're just going to start at the beginning of the file and just read your way through the file. Never read and write from the same file. Writing a file that already exists is going to clobber the old version of the file. You've got to be careful about that. If you want to write to a file, if you have opened a file for, let's say, a faut equals Fopen, some file name, comma, W for writing the file, just like we had the printf statement that prints information to the screen, fprintf writes information to the file. You just provide it also with the additional argument of the address of the file that you're trying to write to. Pretty slick. And because this is all being done in ASCII, you can use something like VI to actually open up the file that you are writing and seeing if your program is working. Now I'm going to show you some stuff on the screen in just a minute here, but you'll be able to see that you can make a copy of this file that I have, like decoded data, and you're going to be able to do reading and writing from their file as part of your assignment. There's going to be 10 observations in that file. The format of the data is explained to you in the textbook at the assignment at the end of this chapter. I believe we're on assignment 7. And for each of the 10 observations, I want you to read the observation from the file and use the metcalc.c library to compute relative humidity, potential temperature, and wind chill. If you have to make any assumptions, like for example, I'm not 100% certain that I give you the pressure, you might have to make assumptions when you compute things like potential temperature. Just document that that's what you did, and I'll be happy with that. And write your output instead of to the screen. And feel free to write it to the screen too, but write it to an output file called my.output, just to show me that you know how to read files using the fscanf function and how to write files using the fprintf function. Okay, I'm going to make a couple quick changes over here, and then I'm going to bring up a terminal session, and I want you to see, we'll do some examples of reading and writing from files.